Perfect. So today's lecture is, as I told you, you are not here at that time, but the idea is to make it a bit, again, short. The Monday one would be longer because it would be like an end-to-end pipeline of the NLP process. But today we want to also, again, keep it short so that you can go earlier because you voted for. So today's topic is about transformers. Basically, there is a new architecture that was announced a couple of years ago, and now a lot of advancements in the domain of deep learning are revolving around this area, not only in NLP, but also in vision. We will first start with providing you the motivation for the architecture, what is new in this architecture, and then we will see two examples in total. One would be today, which we will see one example of how transformers will apply, and the other one in more details would be on Monday. So that's the general whole idea. Let's get started. First, start with boring the slides. Again, you remember everything about the deep neural network, as we said also yesterday. The idea about deep neural networks in a normal way is that everything is sent in parallel to the network. So we don't have any kind of positional or data for every time series. We sometimes say we don't have positional encoding. It means that in the way that we encode the data, position in time or position in the space is not considered. So everything, basically the features have equal importance in a sense, and they don't come after each other. So this model was not very useful in modeling things that are one way through the time. If this was a time series data, as we'll also see later, it was not useful to model it with a neural network because neural network attends to everything in the input at the same time, instead of doing it, instead of just attending to the data points that have come before a certain time. So that's how these networks had a problem, and we aim to solve it. I don't think I will go over CNNs again, but just I will say something quick about CNN because we will return to it back later after we introduce transformers. In the idea of CNN, still we have the network in the end, and this is a very important part. When we add a new architecture about neural networks, we don't get rid of the fully connected layer idea. There is usually always a fully connected layer in the end that converts whatever we have found through the process into a final output that we can show to the user. Like imagine in CNN, we do all the convolution and pooling. Or imagine, I don't know, in RNN, we do all the recurrence. In transformers, we will see what we do. Like we do something, we do a lot of stuff about feature extraction, anything here. But the output of this layer is not what we want. For example, we want to classify if the image is from, for example, it's an image of identifying plants to find if they have a certain disease or not, based on the shape of the leaves, something like that. Or we want to have a picture of a group and say if they're happy or sad. It's the classification task. What we get at the end of feature extraction is not a binary label of 1 or 0. So in the end, we have to add a fully connected layer with the output that we want to achieve what we want. So here in this example, you have 3 different outputs. Here, for example, you can use it for the multi-class classification. Imagine you want to classify a certain a picture of a leaf of a plant into having 3 types of diseases, if they have of those diseases or not. What you do is you have 3 output nodes, and each of them can have a probability, for example, of having a certain disease. And then you can calculate from there if the plant, which disease is most likely for the plant to have. Or anything you want. You just change the last part, and you keep a lot of this the same for a lot of tasks. That's the general idea that just you need to have. We will also use the same idea for transformers. Any questions? I think it was pretty fine. So basically, we have the fully connected layer in the end, and that's what makes it important. Okay, let's move aside from CNNs for now because we are not deep into CNNs for today at all. It was just a quick recap. We introduced the time series task. Again, a new recap slide. What we learned yesterday is that we can model lots of data that come in the sequence of time. We can say they are time series data. And importantly, text was also a time series data, which will be the focus of Monday, next Monday. You can either classify or forecast time series data. There is a specific rule here. We said RNNs or any kind of recurrent networks, or even transformers, as we say it today, are suitable for time series. Does this mean that every data that can be solved by transformers are in the time series data? Not necessarily. You can also use these methods, for example, transformers, as we will see. We will see the architecture. You can use all of these time series methods also on non-time series data, in theory. But they might or might not work well in some situations. We will consider some examples, some today, and mostly on Monday. So yeah, and as another tip, if you want to find the data, I think this was also in yesterday's slide. If data semantics, the meaning of the data changes by changing the order of the data, it's a time series, and then you are pretty sure that which model you want to apply. So recap done. Now we want to introduce transformers, but we introduce transformers based on RNNs because we start from RNNs and we add and remove some components until we reach the architecture of transformers. So let's say it together. We had the recurrent neural networks. We had a lot of cells. We had a set of input to each cell that were actually the data at each time series. Each of them can also be a vector like in practice, but here we are dealing with simple data points to just show a point. And each cell has an output and also passes a hidden state to the next cell. And that's how the recurrent network was made. It's actually a recurrence, but it's unfolded in time. Very simple. We then found issues with recurrent networks. One of the issues was the problem of vanishing gradients or exploding gradients in theory. When you have very long range dependencies, imagine a long text, or as we will see later with also image data, you can apply RNNs and we'll see how. Imagine you have a big image or basically a lot of patches of images, and you want to change the output of a node on those ends based on something that you saw in the beginning. As you may remember from the example that I live in France, and then later you want to predict which language they speak. And because of the problem of not being able to model long-term, long-range dependencies in RNNs, the model tends to forget that you were actually talking about France in the beginning, so it fails to suggest French as the most probable answer, or anything like that. We always want to ensure long-term dependencies are indeed measured. It's very important, as you will see also in text, because we naturally work with lots of data. For example, we want to extract something from a long Wikipedia page. We want to search something, and the model should be able to attend to the beginning of the page. However, a simple RNN may even struggle to attend to, I should not use the word attend because that would be another meaning soon, I won't say pay attention, but not that as well, to basically consider the word in the beginning of the sequence. The idea is prevent this from happening and make the model able to consider all of the sequence at once. We saw there have been solutions in the line of fixing this problem. One of them that we saw, which was actually successful and a lot of people used it, however, came with its own disadvantages, was LSTM, long short-term memory networks, or LSTM networks, in which we still had the general recurrence way of making an RNN. However, we had a steady state that was transferring between all the cells in the network from the beginning to the end. And we had different gates in order to change the value of the cell state. We could have played with how are we going to update the cell at each time and how we are going to reset the value of the cell at each time. So basically, how we are going to change the value, as well as we had an output gate here to measure from the combination of the current input and cell state, how much do we want to output. So by controlling these gates, which would actually happen in the training phase, we were able to train a model that is in theory able to better manage long-term dependency. However, they are still not the best way to manage long-term dependencies because there is still a set of operations taking place, and we are just adding tricks to fix this. Imagine like it's a city, and you want to, for example, imagine it's in Lausanne, and you want to go from Puy to Renault, like a long distance, and then you can say, okay, I either take the metro, which is it stops at every stage. Not Puy, actually, I think it's Flon, yeah. From Flon to Renault, you take the metro that stops at every place, and it's a bit long. You can do tricks, for example, go to, for example, the Gare, and then use the SPD. It's faster, but it's still some steps, right? So we are not fixing the idea. We are just adding shortcuts, in a sense. We are not inherently fixing the idea of being able to consider long-term sequences. So that's the thing. But however, LSTMs were successful for a long time, so we are not bashing them here. They have their own problems. For example, they are a bit complex to build and to train. like to build, not nowadays because PyTorch take care of all of that, but at least to train, they are computationally expensive. There are a lot of different functions that you should run here. And also we saw that interpretability is also a problem because we don't know exactly the meaning of each of the values here and how they are gonna affect the decision. If you want to make a system, make a tool or a website or a platform that predicts something for people and gives them suggestion from AI, you should tell them why this suggestion is valid and why what should they change in order to improve based on the metric that you gave. I said the example of Grammarly. Another example that actually it was a research project in our lab as well was that imagine you want to make a plugin for Moodle and you want to ask a plugin for Moodle that would predict if the students would fail or pass the course based on their interaction with the course in Moodle, something like this. And you can actually do this. We found in the lab that you can actually do this. If we see people don't open the course material until the night before the exam, it's more likely that they are going to fail the course or things like this. However, if we apply this plugin in Moodle and then we just tell the student, you are going to fail this course, they may just panic. They don't have any idea what to do. We should strive to find ways that we can make our models explainable and interpretable, so that we know why the models predicted something, and then we can, for example, tell the students or tell anyone who is using our tool, like in Grammarly, normal users, or anyone, to what to improve. So this was the problem of LSTM as well. Transformers don't fix this problem as well. Like Transformers is not the best solution. Like it just helps in fixing these problems. It introduces its own problems, first of all, and also there's still shortcoming. So all of these are still active research areas. However, we will see one method that would mitigate a lot of these problems. Any questions from the recap? I think until now it was just a recap or something. So fine. Let's go. Okay, before getting, we should first think of an architecture that people use for RNNs, for now just consider RNNs, in order to make systems. And that's called sequence-to-sequence models. What does that mean? In a normal RNN, you have a set of cells and you have inputs and you measure the outputs at each step. Which makes sense, right? You can do time series prediction with this and it works very well. However, sometimes we really might want to have an effect on the future words on the previous word. What do I mean? Imagine you want to use an RNN for the task of machine translation, like Google Translate. You want to translate, for example, Je mange un pomme to I am eating an apple. You want to translate French to English. Just consider this example that I just said. This example is not very good. I wanted a better example. I want an example that the order of the words are different. So sometimes in some languages, when you are translating from a language to the other, the subject comes in the beginning, the verb comes in the end, or the order of the words might change. Oh, for example, a good example is that, for example, I think in French, the adjective comes after the noun, right? Those of you know French. If I'm correct, right? Could you give me an example? Because I'm not good in French. Like, for example, you want to say a big house. You say a maison grande, right? You want to say? Depends. It depends. Like, I think you sometimes swap them, right? Sorry?
Yes, it depends.
It depends. It's not like it depends on the case, exactly. Because I don't know French, sorry. I want to say something from one language and I say no one knows. So in French, you sometimes swap. And the thing is, imagine you are doing here. You are just using this. You want to, for example, here, first you say the adjective and then the noun, and you want to have them swaps in the translation, because otherwise the translation does not make sense. However, when you are outputting here, it has no idea of what's going on here. So while some data could be modeled as a time series, it's sometimes also useful to be able to see future inputs. Because sometimes when you are, this mainly happens when you're transferring a time series into another time series, like translation. You change the order of the words, and then you want to reflect that. Like if a certain word in French might come in the beginning of the sentence, but in the translation, it might come at the end of the sentence. So you want to make sure this is happening. And for that, if you just start from the beginning and just do the output, if this is the word that comes in the source language here, You can't predict it here because here H0 only depends on X0 and does not depend on X2. So this makes a problem. You can't make a good machine translation model with RNN. It would be very bad. I hope you understood what I mean, right? I think it's so. For this, researchers started to find ideas to how we can make it work. One idea is to make a sequence-to-sequence model. What's this? You split the whole network into two parts of RNNs. One, we call it the encoder part, and one, we call it the decoder part. In the encoder part, it's very simple. You input the input as you provide the input, as we already did. However, you don't care about the output of each of these cells. You don't care at all. You just care about the output of the last encoder. And you agree with me that the output of the last encoder depends on, there's nothing in chat. You agree with me that the output of the last encoder depends on all of the inputs, because the output here depends on this and this. This one also depends on this and this and so on, right? So, and the output of the last cell is somehow a summary of the whole input, in a sense. Because like it's a weighted average. I know it's not a summary regarding what we call a human summary, but it's somehow so it's basically a compressed version of the whole input. Imagine you are zipping a file, you're compressing it whole into one vector. That would be the output of this cell. Then what we do is to have another set of RNNs, and here we pass as input to the first RNN cell the output of the encoder, the last encoder, and then we don't care about the inputs. We just care about the state that is moving between the cells. And now we consider these outputs as the real output that we have. So the difference here is that we just split this thing into two parallel lines, one line of encoders, then we get the last output, and then one line of decoders. The benefit that this approach has, of course, there is a downside because it's like more RNNs need more time to be trained and everything. But the good thing is that here, all decoders have knowledge of all of the encoders. So all of the output values can depend on all of the input values, because all of them start with here. And okay, when Y1 depends on this, of course, Y2 also depends on this. And of course, Y3 also depends on this. So by using this kind of, we call it sequence to sequence, because this is one sequence and it's also another sequence. This is mostly useful for tasks that you want to transfer one time series to another time series. A good example, like I think the most famous example is machine translation, because if you consider text as time series, you want to convert in a French to English or another language. There are also other tasks as well. For example, another task could be summarizing a document. Imagine you have a very big Wikipedia page and you want to summarize it in one paragraph. First, you have a long encoder that would encode all of the words in the Wikipedia page. You pass it to a decoder, and then you have some decoders that would decode the words of the summary step by step. And it's useful because in summary, you don't necessarily follow the exact order of the Wikipedia page. You may, for example, imagine this is imagine a Wikipedia page about EPFL. It starts with where EPFL was founded, then it goes to the current administration, then the number of students. In your summary, you may start with the number of students. You may start with EPFL is a school in Switzerland with X students, and it might come in the end of the document. So it's always a good idea, like as a human, to first read the whole document and then try to decode it. That's what sequence to sequence does. It somehow reads the whole document, reads the whole time series, and then gets the last output to do all the decoding. Any questions? Is all fine? So this is the concept behind sequence to sequence. What do you think can be some issues here? Like not issues that we also had in RNNs. We also had some issues in RNNs, right? Generally. For example, they are a bit more complex to train. They are not like that. Like, do you see any other issue that's unique to sequence from what you see here?
It takes too long.
Yeah, exactly. Yeah, it takes too long. That's true. But this is somehow also general of an RNN as well, right? If you also had an RNN sequence that were 8 cells, it would be practically also long. So this isn't something that was introduced by making it sequence to sequence. RNNs and sequence to sequence are both long, both take long to train. So, but that's indeed the problem. And transformers does not fix that. Actually, it makes it worse. Like transformers usually even harder to train. So we are not trying to solve that. We just solve that these days with buying more GPUs actually. So yeah, that's not that's the issue. But okay, let me say it. One issue is that the whole data, which can be very long, imagine a whole Wikipedia page, is compressed in just one vector. This one vector and the end of the encoder series should represent the whole data, and that's not possible by theory. Like how can you represent a very big time series in just one vector? No matter how big the vector is, you lose some data. And this data loss can be harmful because imagine you want to translate something. If you compress a whole sentence into one vector and then you try to translate from that one vector, you are losing some words. You are losing some. You are possibly losing some information, and that's harmful because we want the translation to be truthful. So one idea is that might come to your mind. Why are we using just the last encoder output? Why are not we using also stuff in the middle as well? Because they're also in data output here, right? And that's basically the main motivation behind transformers. But the question remains, okay, if we want to use them, which one should we use? How much should we use the first one? How much should we use the last one? And there are a lot of questions here, right? So let's see how researchers started to tackle this problem. A new method today, surprise, surprise. So this is usually the famous question that you see, which school is it? Of course. What did you see in the picture in the beginning that led to you that this is EPFL? Each of you. Like, what's the main thing that you saw in the picture that you thought is EPFL? Sorry? Rolex. Exactly. I think Rolex is a big thing. Maybe the lake could be also an option, right? This is how our brains work. When we see something, when we see a picture or a time series, we don't try to compress the whole picture into one vector and then we try to analyze it. We look at the image or the time series or the text directly and try to find where in the picture or where in the time series is better to attend to, is better to pay your attention, that is more useful for your prediction. When you are thinking about pictures of a school, you always first think about the landmarks of the school. Like when you want to classify a picture as EPFL, you first see, and you don't, for example, see here, like the grass is here, because almost all the schools in the world have some park around them that is green. You check the unique buildings. You check the Rolex, for example. And then you say, okay, Rolex is a unique building, and then your Rolex is from EPFL. So basically, your mind puts more attention to Rolex. Imagine if you convert this picture to a lot of grids, like a small grid, and each of them have a weight in your mind to how much do they contribute to the classification output. The square here has the maximum weight. Maybe the square here has also a weight because for me, it's always like seeing the lake just makes me think of EPFL. Not a lot of schools are close by lakes. But the square here has no value almost for you because it does not influence your prediction. So the concept is that different parts of a picture or of a text have different influences on the output. And we want to somehow model this by using matrix functions. And we call this the attention mechanism. That's how they applied this idea into deep learning. As I said, it's not only about image. If you want to classify text, like imagine you have an open book exam and you have a certain question and you want to find it, for example, in the cheat sheet to find the formula. Of course, you don't pay attention to the commas and these kind of weird normal characters that are in the cheat sheet. You pay attention to the topics, to the bold parts, to the formula that you have in your mind. So our brain puts different attention based on the different tasks that we do. Sequence model does not allow us to do that because we are compressing everything into one vector and we are just using that one vector to decode. And we can't, if we compress this to a one picture, we might even lose Rolex. It might be compressed into a lot of buildings in the center, a lake on the side, and some grasses. And you can't for sure say it's EPFL. But you have access to the main input. You can just pay attention to your Rolex and say it's EPFL. So you got the idea, right? What? Perfect. So until now, as I said, the final encoding step had to represent the whole sequence into one vector. That was the challenge. We have information loss, and we had to do the whole decoding from a single vector, which is again information loss. The idea is that we add an addition to the architecture, helping it to attend to the different inputs in the sequence. And by that, we look not only of the hidden state of last encoder, but at the hidden state of all of the encoders. Let's see here. This is the vanilla normal encoder-decoder architecture, or sequence to sequence. You also call it encoder-decoder. Set of encoders, value pass, set of decoders. Here you have attention mechanism that you can see there is still this line of encoders and line of decoders. They are still RNNs, they are still time series data. However, for the input of each of them, you remember there we didn't care about the input, right? They were just random inputs or pre-initialized inputs. Here, we put the input of each decoder a weighted sum, linear sum of the hidden outputs of each of the encoder layers. By this, the model, for example, can learn which part of the encoder should be paying more attention to. It just increases the weight of that part in the weighted average, in the weighted sum. And that's how the attention practically works. So this is another more fancy way to see how it's exactly done. It's not just a simple weighted sum, but also there's some functions going on there. So the encoders, they have hidden states. They all come here. We have a feed-forward network here, a simple network that would just transform. And we have the softmax, which we'll talk about it, I think, on Monday. Softmax, for now, you can consider it as something that converts a set of values to probabilities. So makes them between 0 and 1. It's like sigmoid, but for multiple values. We'll see it later. And then we have a weighted sum. This is the sign of weighted sum, the sum and the multiplication. Weighted sum of the inputs that are basically passed here. You do it both with the inputs themselves and the input passed through a network. This is how it's applied in practice. And then there are 4 values. Here there are 4 values, it can be more. And you just pass them to the decoders. So we know that in each RNN cell, there is one value, the hidden value from the previous cell, and one input. For input, you give the C1, C2, C3, and for hidden values, you just give the one from the previous cell. For the first one, you just initialize them S0. That, yeah, basically you initialize it for an S0. So, any question here? So this is how the attention mechanism works. Fine, yeah, perfect. So this is another variation of the attention mechanism. It's actually a very nice book. Later, after the bootcamp, if you want to really learn about, I mean, it's a bit old, I would say. Like it's 2022. You may say 2022, no, it's not old, but in this field, it's very old. Like I think half of the methods are not the state of the art anymore. But it's a very conceptual book. Like it's a very nice book. It's from Tonsal. It's named Natural Language Processing with Transformers. It's mostly about NLP. But you can read it after the bootcamp, maybe. I would suggest you to read it. That was the book that introduced me a lot to these kind of things. It was one of the motivations for me to do my PhD, actually. So yeah, I like this book. In the book, it's written that the main idea behind attention is that instead of producing a single hidden state for the whole input sequence, the encoder output the hidden state at each step that the decoder can access. I mean, I've said this multiple times to you, but yeah. You can see an example here. Again, we have RNN cells. This is the translation, exactly the type of translation. Transformers are great, and it wants to, I think this is German. It wants to translate it to another language. And actually here, each of them have an state. And each RNN cell has uses the combination of these states. For example, you might think, why is it useful here? Because this is direct mapping, like transformer is translate transformer or transform to scene and so on. However, in some languages, verbs are different based on the like the gender of the noun or things like that, right? There are different grammatical rules. For example, here maybe in some language, based on if the transformer is feminine or masculine, it could be different that which verb used here. So it's also useful if this verb can attend to the different parts of the input to find what would be the correct translation. And here is exactly the same. So each RNN cell gets input from the previous one as well as a weighted sum of the states. Any questions? I can also check the chat from time to time. Seems fine. Okay. So we call it the attention mechanism. And people tried adding attention mechanism a lot to different RNNs and actually saw improvement, because I told you, like, some tasks were actually not even enough feasible with RNNs, like translation, because you needed to also pay attention to the future token sometimes. But with adding the attention mechanism, it became easier to do, but also more complex. So a nice point about attention mechanism is that we can get, as I told you, some intuition or interpretation of what it does. We can learn the alignment of the inputs. For example, here, there is an example. The agreement on the European Economic Area was signed in August 1992, l'accord sur la zone économique européenne a été signé en août 1992. So you see, it's just a translation. You should have said 1992 in French as well, but yeah. So as you can see, there are this is the colors here are a visualization of the weight of the attention links. You can see that each word is actually putting the weight on the word that is the direct translation of, which is what we want to. Here, for example, they is mapping the agreement is accord, which is what we also expected, right? However, you might see some weird stuff going on here. Why it is not just linearly going like this? You might see some weird stuff in the middle. And it actually makes sense because you see, it's exactly the example that I wanted to tell you, but I forgot. European Economic Area is translated to Zone Économique Européenne, because in French, the order is different. Our names could not have captured this well. However, here is attention layer, so it's easily captured this and find that European is matching with European and has the maximum weight here, and economic with economic and so on. But you can see there are also some kind of gray things here, which means that, of course, the model is a bit struggling because the order is different, but in the end, it was able to find the agreement pretty well. And if we didn't have attention for the RNN, we couldn't have done this. So fine. You got now the idea. And this is also useful because we can visualize. Like this is useful because if you want to debug what the model is doing, and we have no idea if it's doing right or wrong, we can visualize and see which tokens are attending to which tokens, and we can debug our model to find problems. Perfect. Yeah, very cool. And I also have to say, you don't put the attention weight yourself. Basically, everything in these kind of networks, all the weights, all the weighted sums are learned automatically in the backpropagation. So if you use a lot of training data, it would automatically learn the patterns and adjust the weights such that it would make perfect attentions based on every input that it has. So in practice, it works well if you do the backpropagation. Any downside that comes to your mind? Like anything, just say anything. Of course, there are some obvious downsides. And actually, this is also one of the obvious ones, but I mean, you can have a lot of downsides. Some of, like, one is very obvious, like you just added newer stuff to the model, so it takes longer to train. Of course, yeah. But we don't want that because we have GPU, so it's fine with us. There is one big problem. That was also a problem in RNNs. Any idea? I mean, you can just say something, fine. What do you think is the problem with this? Imagine you're in a company, you made this, you're a boss of a company, and your employee made this, and you want just to bash the employee. What do you say? I can also say this if nothing, 15 seconds. I just want to ask you.
How to keep the order, like we're passing all of them at the same time?
That's a good point. Very good point. And actually, yeah, so in normal RNN, I mean, this is not the downside I wanted to say, but it's a good point. So let me address this first. In a normal RNN, the order was very obvious. It was always ordered. Here we are adding the weighted sum, and here the order is violated because it's just a weighted sum of all of this, and there's no order here. However, it's still because we have the sequential thing here in RNN. Each of the states implicitly contains the order because each of them also depends on the previous cells. So as long as we have the chain of RNNs here, we still can model the order. And in practice, this didn't turn out to be a problem because it's still this state 4 not only depends on this cell, but also all the cells. So in practice, this didn't turn out to be a big problem, but you are right. We are decreasing the role of order of the words a bit, but in practice, it's fine. Yeah. Actually, in some it's not fine. Like maybe sometimes you add attention and the model actually gets worse. Or even transformers, as you will see now. Like we had one paper in which we did it, and we saw actually RNN work better than transformers in that example. LSTM work better than transformers. So it's not always that whatever we say is better than the previous one. It could be. So there's one thing here. Let me say to you that really bugged people because people started after being attention mechanism and saw how powerful it is. Companies, research labs started to train lots of big models, but there is always a big problem here. Each cell depends on all the previous ones. So you can't have any parallelism at all. And this is something that bugs computer scientists a lot. Maybe if you have courses on like distributed algorithms, these kind of things, the idea is that we want to do things in parallel because we have multiple core processors. So we want to be able to do things in parallel. And this certainly limits us because we can't do anything here until we have processed here. And we can't even do anything here until we process all of this. Because this also depends on the state 4 in the attention mechanism. So after introducing the attention mechanism, basically the whole parallelism is gone. So people were thinking how we can add the parallelism. And they had a very weird idea at the beginning that you might think what a crazy idea this is, because we are literally backtracking on all the decisions that we made. But that actually turned out to be very successful. And that is to just remove the links between the RNNs to make it parallel. So you might say this is not an RNN anymore because RNN has a recurrence, right? So it should be linked. The idea is that instead of these, you just have normal cells that are not recurrent, but you keep the attention. And then the model, let's see how it works. And interestingly, not only the model was able to do more stuff in parallel, but actually the accuracy got better. And that's what we call it the very first transformer architecture. So in the transformer architecture, you remove the connection between these, so they just convert to a normal neural network, not an RNN. So a normal cell is not an RNN anymore, it's just a neural network. You have again the encoder block with all attention and everything, and then you have the output, and then you have again the attention, but there's no RNN here. So you remove the recurrence altogether. You got the idea? You got what they did. So you may directly say this is the downside here because we lose the order. And that's true. And then they had to find some way to introduce the order back, which we will talk later. But for now, ignore the order. Imagine the order of the words is somehow fine. We will say how did they fix it. So yeah, basically they call it. This was this very famous paper that attention is all you need. Maybe you have heard about the name of this paper. It's like maybe one of the most famous papers in recent time in computer science. They said you don't need recurrence. Attention is all you need. And they showed better results compared to models that were developed before the attention era, before the transformer era. What do we call it a transformer? Because basically somehow we are transforming a sequence into another sequence. So that's maybe not the best thing, but when we say transformers, we mean an architecture that does not use RNNs. It just uses normal neural networks, which have the difference in RNN is that there is no link here. So we don't have the link between the NMs, and we just have the attention. So we have an encoder block in a transformer and a decoder block. The encoder block gets the input, again does an attention, so we have two attention types, 2 times attention here. One is the first attention that each of the neural networks attend to all of the words of the input, and each produce an output state. Then the decoder block looks at the output states and then transforms it to the final version. So we don't transfer all at once. We first transfer the input sentence into an internal state that this is not human readable. This is something just a bunch of numbers for the model. And then a decoder can transfer it to another version that is readable by the human, that is our target. So if you do it for the task of translation, for example, English to German, you input the German here, you get a set of values here which don't mean anything to human eye. It could be like 0.5 minus 0.6 or just a bunch of numbers. And then you give them to the decoder, and the decoder would output the German version. So here we have 2 parts, and each part only specializes in something. The encoder part only cares about converting English as best as it can to an internal version, and the decoder block just cares about converting that internal version to German, and it does not care about English. So we are splitting the role of encoder and decoder. It's like when you want to talk with someone, but you don't know their language directly, so you translate to English, and then you have someone that talks in English and their own language as well, and then you use them to talk with that person. So you use another middle language as the proxy. This is like the language of the computer or language of the deep network, as you might call. Encoder transfers what we have to that language, and coder translates that language to the output. And finally, input can be anything. Here, the example is a sentence, so it's text, but it can also be images. For today, we will see a practice of how the images do this, And then for Monday, we will go deep dive into text, and we'll also code an example of doing this in text. Each of them have certain small details to take care of. Any questions? So you got the whole idea? Fine. Easy, hard, difficult, fast, slow. I should say all that in adjectives. Okay. Perfect. So also, I have to say that you don't necessarily always need to have the encoder and the decoder. Sometimes you're only fine with one of them. Today, we won't go over that, but on Monday, we will see two examples of an encoder-only model and the decoder-only model. And I don't know if you have heard about BERT. BERT is a famous example of an encoder-only model, but you have certainly heard of GPT, which is an example of a decoder-only model that we will see how it is made on Monday. So like basically GPT is also transformer-based, as you might have guessed. So let's explore how transformers are designed. We can continue a bit. I think it's and then we'll have a gap at 5 maybe for 10 minutes, and then we'll come back. In practice, as I said, we have a set of encoders and a set of decoders. You always provide the input, the encoders try to encode it. And sorry, you have a, sorry, let me start from this. Before saying that, this can be done in parallel, right? Because there is no dependency between them. So here you can basically each of them attend on all different tokens at the same time. So you can do all of this in parallel on different processors, and then you have stop state. Then you can do all the decoding in parallel. So you can't do encoder and decoder at the same time because decoder needs the output of all the encoders. However, what you can do is to do encoder and decoder themselves parallelly. So just do the encoder in parallel, then you have the results, then do the encoder in parallel. However, people thought that it is still not enough, and they want to have balance. So they said, why don't we repeat the encoders? We have multiple encoders that they connect to each other with an RNN style, but inside each encoder, we can do it parallelly. So that was the general idea that was also used in transformers. In practice, you have multiple encoders that also depend on the previous one. But inside each encoder, there are a lot of cells that don't depend on the previous ones. So we don't have any RNN cell here. Inside each encoder is everything feed-forward neural networks, just normal neural networks that they don't depend on the previous one, but the encoders themselves depend on the previous one. So inside each block, you train in parallel, but the blocks themselves are not trained in parallel. And this is fine, because we don't have a lot of encoder blocks. In an RNN, we might have, I don't know, in practice, maybe you can design a network that has 10,000 cells. And that's very difficult. But here, you only have 1, 2, 3, 4, 5, 6, and each of them can be run in parallel. So it's in practice equivalent to 6 cells. Imagine you have a lot of CPUs. So regarding time is fine. It's just the resources that you need more. You just read to knowledge 6 times instead of 1,000 times, because each of them have a lot of cells inside them that are not in parallel. Any questions? So you repeat the encoder block. Remember, this is not an RNN cell. This is a full encoder block like this. Like this blue thing is just a green thing here. Encoder block. And then each decoder can attend to the all previous encoders, of course, and provide the output at the end. We just take care of the output of the last decoder, which would be ideally the translation of the input sentence, if we train the model well.
Excuse me, like
Yes.
there's many encoders, right? And we are like all mixing up all of the sequence, and at the end, like if we have many encoders, don't we just like mix up the data that much that it's really difficult to recognize any patterns or something?
Exactly. So there are two patterns, there are two aspects to this. First, mixing up regarding losing the order, which we will cover it. Don't today. We'll cover it today, how they fix this. So there is a very nice way to solve the order problem. For now, yeah, if you just code whatever I said, your model will not work for time series because the order is messed up. However, regarding ascending to the previous tokens, we expect that if we train the model, if we fix the order problem, we expect that if we train the model with high enough data, the weight of these connections would be in a way that the model would learn not to be confused. And that's why we generally say, this is a general rule of thumb, it's not proved, but generally, transformers need more data to be able to train compared to RNNs or simpler models. because there is a lot more weights and connections here, and they should be carefully designed so that they are not confused on which encoder input we are using. So for that, you need more data. If you train a transformer with a very small data set, your results may be even worse than random. Like they might be very bad results. So you train transformers on very big data sets. Actually, we'll also come to it on the NLP week to see what OpenAI did for the first time. They literally scaled to train transformer on almost the whole internet or a big bunch of the internet, and that's why how GPT-4o is like very good at answering questions. So the more data you have for a transformer, the better the quality is. But yeah, exactly, you are right. But regarding the order, we will see how we solve it. So no worries about that. Is that fine?
Yes,
Right.
thank you.
Yeah, perfect. We'll get to the order. So okay. So let's move again a bit and then okay. Maybe I will go to this slide and then we'll have the gap. I think it's better. So let's see this first. In transformer, as we said, we had an encoder and decoder. So encoder, we have the self-attention. By self-attention, is basically the weighted average of the inputs. You can consider it like that. And a feed-forward network, as we saw, right? So it's pretty obvious. And for the decoder, we have again the self-attention. We have the encoder-decoder attention, which is, so encoder-decoder attention is here, this line. Because each decoder has to attend on both what's coming previously and on all of this. So we have two attention layers, which means we have two weighted sums. And then we again have a feed-forward network. Did you understand this? It's just two different weighted sums. It's nothing very fancy. So there's a big difference between encoder and decoder, because in decoder, you not only attend to whatever is coming before you, but to attend at the same time to all of the outputs of the encoders, as you see here. So you attend to both, so you need two attention layers. But still, in the end, you have one feedforward layer. I mean, this is simplified because there are also more components that you will see. You also have layer normalization. We will also get to it. That we had a quick brief discussion about it yesterday. We'll also have it here, but yeah. So this is the general architecture of an encoder and a decoder. In more details, these are the inputs. For example, this is the thinking machines. I don't know, like translation maybe or something. I don't know what the example is from. So they want to they want to give this input to the model. This is an encoder block. You give the two inputs to the self-attention layer. This layer just basically calculates a weighted sum of these inputs. You get two outputs as two things as output. Each of them is a weighted sum or average of these two inputs. That one and the two do not have any meaning. They are not real world. They are just a bunch of numbers. Then you give them to two feed-forward neural networks that are independent. This is not an RNN. We don't have a connection here. There are two independent networks that you can train them simultaneously at the same time so that you can parallelize. And then you get two outputs that you give to the next encoder. In practice, there might be more. Like these are not only two, because if it was two, then there was no point in parallelizing, right? But in practice, there are more. And you give, again, two outputs of this block. You give them as the input to the second encoder block, which is exactly the same. And you repeat this pattern until the encoders are finished. Is that fine? So in practice, people just trained it, just as a quick example, and saw the attention layer. And as you can see, you can even visualize the attention at this step. Attention is usually an easy thing to visualize because it's just a weighted sum of inputs. So you can see which words attend to which words the most. And then you can see, you find patterns in the data, which obviously is always useful. So again, this is just a recap before going to the break. The main difference is that, as you can see, the state is the same. We have, again, the same encoder and decoder architecture as in every sequence to sequence thing. There are two main differences here. First, we got rid of the connections between the cells, which means we have converted RNNs to normal neural networks. And second, here, we are inputting the data to each neural network also with an attention. So that it's not like first neural network only takes the word transformer, second one only takes R. Because then you lose something. Here, this RNN cell somehow sees all of the inputs. And we want to also ensure here each of them also see all the inputs. So we just have an attention block. So there are two main differences. We got rid of the recurrence and we added another attention blocking encoder. All fine? Perfect. So I think it's now 5 for 59:47. Let's maybe have a quick break and if you want, and We'll continue in 5:10. Okay, should you go? Let's go. So, 3, 2, 1. Okay, what did we see? Did you see that? We saw the difference between the RN and the self-attention. Now let's get a bit more technical to see how it is calculated in practice. Then you see the final architecture of the transformer model, and then we will see one example today about vision transformers, and then we'll go Monday in more details about the text. So let's see. First, start with the self-attention process. That's basically the core somehow, because the feed-forward network that you had here is not core, right? You already know how the feed-forward network works. This is pretty basic. Just a network with a certain number of layers that you specify and do on the works. Here, the self-attention is more important on exactly how this weighted sum is calculated. What I'm presenting now is just the thing that works. It doesn't mean that it's the provable version that works the best or the optimal version. It's just something that works, so people are using this version in practice. First of all, you have the input data, right? Thinking machines, like the same example that you had, it's just a sentence. First, these are words. These are normal words, so you need to convert them to something that could be understood by a computer. Usually convert them to a vector. For example, we can find the vector x1, which means thinking, and then vector x2, which means machines. We don't now care how do we make these vectors. We will see them on Monday. However, imagine we have a process of converting those words into vectors. We call those vectors embedding. Perfect. So now we have our input data in the form of vectors. If it was already a vector, it's fine. If it's not, we convert it to a vector. Then we create 3 new vectors from each of the inputs. We call them query, key, and value vectors. So how do we find them? You know how to convert the vector to another vector. You multiply by a matrix, right? So this is how you do it in linear algebra. We have 3 matrices, WQ, WK, and WV. And we use these 3 matrices to transform the space of the embedding space, into query vectors, key vectors, and value vectors. That's the pretty standard version. Usually, it can be the matrices that have more rows than columns, which in practice, it means that the length of the 3 vectors, queries, keys, and values, are in practice smaller than the input data, which is somehow a kind of compression, because you're compressing a bigger vector into a set of smaller vectors that can also help with the efficiency and the running time of your model. So first of all, use 3 matrices. The weights of these matrices are anyways learned in the backpropagation process. So you don't define it yourself. Like what are the weights of W, Q, or WK? You don't verify it yourself. You just let the data do it. Perfect. Then, when you have the query key and values, for each input, for each of the input, we multiply its query to all of the keys. So the query key and value are just names, right? They don't mean something else. They're just 3 vectors made. We just call them Q, K, and V. We multiply the query vector of each input onto all of the keys. So for example, here we calculate Q1.K1 and Q2.K2, and we store them. Both of them are related to the first input because the query is the first. You can consider it like the query in a real like database system. The query is for retrieving something, right? And the keys are the ones that you want to retrieve. So basically, you apply this query to each key and find the dot product. Also here, for the next one, you calculate Q2 times K1 and Q2 times K2, and you store them. So you have now n numbers. Imagine you have n words. You have n numbers of Qi terms, of Q1 terms Ki for I from 1 to n. You have n numbers for each of the values, right? Then here we do 2 tricks. First of all, first of all, the numbers that we find here might be very big. Like we have 112, for example, Q1 times K1, because it's dot product, right? You're multiplying all of the values. So it can be very big numbers, and that can be unstable in the training process. So first of all, we should normalize it and somehow make it smaller. To normalize it, we divide the scores by the square root of the dimension of the dimension of the key vector. So that somehow turns into a normalizing process. This is, again, just an arbitrary thing that turned out to work, right? So we just basically normalize by the square root of length. And then you find a set of numbers which you will then have put into softmax. So now we should introduce what the softmax is. Imagine you have a set of numbers. Imagine you have a set of, I think it's difficult, right? I just tell you. Imagine you have a set of numbers, for example, 5, 10, 15. You want to convert them to probabilities. You might think, for example, we want all of the numbers between 0 and 1, and you want to keep their order. For example, imagine you roll a dice, 10 times it comes 1, 20 times it comes 2, something like this, and you want to find the probabilities. You want to convert a set of numbers to probabilities. What you may think is that, okay, I just divide each of the numbers by the sum of all of them. It is fine, right? Because it converts all the numbers between 0 and 1, and it will be probabilities. However, if some of the values are negative, this won't work. Because for the negative values, this doesn't make sense. The version of dividing by the sum does not make sense for negative values. So you can maybe say, okay, I will use absolute values or a lot of different versions. Yeah, they're true. The thing that they do mostly in deep learning is to use the softmax function. Softmax takes this one. You power e to the inputs, e to the each of inputs, and then you divide by the sum of all the exponentials. Why this works? First of all, it's very easy to see if it is between 0 and 1. It is less than 1 for sure, because the thing on the top of the fraction is less than the thing on the bottom of the fraction. It's less than 1. And it's also more than 0 because the e to the power of anything is always positive. Or 0, or 1. Yeah, it's also positive. Sorry, it's not even 0. So it's right. So e to the power of something is also positive. So you are sure the number is indeed between 0 and 1. And to have something work for a probability, first of all, it should be between 0 and 1. And second, sum of all of them should be equal to 1. This is like the basic rule of probability. And here, actually, when you sum them all, like e to the x1 over the sum of all plus e to the x2 over the sum of all, if you sum them together, you will leave at 1. Because it would cancel together, and the sum of all softmax values would be 1. So this function is a function that will give us values between 0 and 1 with a sum of 1, which means it is indeed a correct probability distribution. So whenever we want to find probabilities overall in deep learning, a very common approach is to use the softmax function, which you can see here. E to the xi over the sum of e to the xi, and here we also do the same thing to convert this number to a smaller variation. Any questions? Fine. So let's see what they did here. So again, we had the scores. We did, as you said, we divide by the square root of the square root of the dimension of the key vector, and then you multiply the values by softmax. Oh, sorry. I got excited. Sorry. You first calculate the softmax. Here we have 14 and 12. To calculate the softmax, you just say e to the power of 14 over e to the power of 14 plus e to the power of 12, for example, or any approach. You can also use, as I said, other approaches of finding probabilities, but what we did with softmax. And then you multiply the softmax with the value vector. That's what you do in the end. So finding the softmax, we used queries and keys. And then we multiply the softmax of each input to the value vector of that. And it would lead to the sum. And this is what we use as the output of the self-attention layer. So let's see why it works. First of all, what do we do when multiplying by the softmax? We are practically punishing those inputs that have low, close to 0 softmax values, which means we are punishing those that have low score. In practice, it means we are removing irrelevant parts of the text, the part that we don't need to pay attention to. When you train the model using the backprop, it would automatically measure this, and it would pay attention to the parts that are most important, and that's controlled by multiplying the value vector by the softmax, because softmax is always between 0 and 1. So it's actually reducing the size, and it can either keep it close to 1, just keep the value as it is, or reduce it to 0. It means removing its effect. Another question, why is this working regarding the sum? And why this is a valid attention? Because here, when you're calculating the scores, it is a combination of each query to all of the keys. So basically, we are attending to all of them, and then we are using those scores obtained from keys of other entries, to find how much should we attend to this value, right? Because that score is used here and then we get into softmax and then using the multiplication. So it's indirectly, in a sense, attending to other tokens, but the way the attention is done is that it checks how much should we attend to this current value based on a combination of all the keys of other tokens. So that's how attention was implemented in practice, and the authors of that paper, Attention and All You Need, found that it's actually very good and works well. Any questions on the general thing? I mean, there are also some specific math details there that different implementations do it a bit differently. So it's not like everyone just does the same formula, but this is the general idea. Any questions? Perfect. So in practice, this is nice and can be done. However, it's time consuming. And you need to calculate all of these vectors and do a lot of different dot products, right? You need to dot product Q to K1, Q1 to K1, Q2 to K2, Q1 to K2, and so on, right? There are a lot of multiplications that take a lot of time. So to make this more concrete and just do it faster all at once, the trick is to convert all of them to a matrix and do matrix multiplication. Because in the end, when you do matrix multiplication, you are multiplying the vectors of rows and columns, right? So if we concatenate all of the vectors into big matrices and just work with the matrix multiplications, you can do it simpler. And then you can just come up with algorithms to do faster matrix multiplication or design a specific hardware or GPUs to do faster matrix operations. And then you can easily train transformers in a easier scale, in a better scale. That's how it's in practice done. So instead of having the individual X inputs, you concatenate all of them in the matrix. You just put them here. And then you have the W, Q, W, K, and WV, as I told you. We still have those matrices. We just, instead of multiplying each of the inputs to one of the matrices individually, we just multiply the whole matrix to the whole matrix. I mean, it's the same, right? If you were a human, it would be the same. But maybe sometimes there are optimizations if you do one matrix operation instead of doing it individually, specifically in GPUs, that is very useful to always convert it into matrices to do it in practice. So you put all embeddings into X, you just multiply, and then you get the Q, K, and V. And as I said, you see, these are actually a concatenated version of all of the query vectors. This is the concatenated version of all of the K, and this is concatenated all of the V. And then what you do in the end, remember, we multiplied each query by all of the keys, right? In matrix multiplication, it means Q times the transpose of the K matrix. This is how it translates to the matrix multiplication. If you just write it in the linear algebra, you will find it out. Then you again normalize it. You put it into a softmax. Here is a specific version of softmax that works in a matrix way, but it's also implemented. You have it in PyTorch. Fine, think. And then you multiply the result of the softmax, which is a matrix of our scores in the value matrix. And then what you get in the end is the matrix, which is again a concatenated version of the outputs of that layer, and then you can give them to the feed-forward neural network to process them in parallel. All fine? So we just converted them to a matrix multiplication, and that is how it is implemented in practice. There is yet another thing in transformers. So all of what we saw were one WQ, one WK, and one WV for the whole sequence, for the whole data, right? So we don't change the matrix for every data point. This is just the base that we are learning. However, researchers found that maybe three matrices are not enough to capture all the data and be able to train them. And we want to, maybe in different training sets, pay attention to different things in the data, not only same things. So the idea was that what if we have different sets of query key and value, and we apply all of them simultaneously, and for example, then sum them together. And that's what they did. We call it a multi-headed attention, actually, which works like this. So we have the input again. We once have a W0Q, W0K, and W0V, and we calculate query key and values. And then we have another set of same matrices, like with the same size and everything, but different values inside. W1Q, W1K, W1V, and then we again generate another set of queries, keys and values. And then it could be even multiple more, like maybe 10 heads, or I don't know. You have we call it heads of the transformer model. This is the terminology called as head. We call it a multi-headed model, or a model with multiple heads. And then we have also the data separately, and we calculate the attention separately in each of the, we calculate the attention separately in each of the different attention heads. So in the end, for each of the heads, which by head we mean a set of matrices for query, key, and value, for each of them we have different outputs. Like we have a Z0, which is the vectors that are input that are outputted from the query, key, and values of the first set, of the 0 set. We have attention head 1 and also up to the end. For example, here in the example, we have 8 attention heads. Right? Fine. And then you may think, okay, imagine we have multiple outputs. We don't want multiple outputs, right? We want to somehow compress them together so that we have one output per input. So we don't want to like have 8 outputs per input, because that would explode the model after a while. So what we do is to first concatenate all of them, put them together, like exactly just paste them together, like this is Z0, Z1, Z2, you put them together to make a long matrix. And then you multiply it with another matrix that you call it WO, which means the rate of output practice. And this matrix also is not something different. You also learn it in the backpropagation. You just multiply, and then you come up, you fix the dimensions such that you come up with a Z matrix that is the output matrix that you want. And this matrix captures information from all of the attentions. And then you can send this forward to the feed-forward neural network and continue. So, all fine? Perfect. So this is called the multi-headed attention. Cool. So what we have here, I have to also say that in the multi-headed attention, the idea is that different heads attend to different capabilities. Because the weights are different. Maybe, for example, in a picture, like in the e-peaceful picture, maybe one of them attends to, for example, natural things like grasses and like lakes and these kind of things. One of them could attend to the buildings and so on. So they're not necessarily interpretable. It might not be always that this head only attends to this and that, but adding more heads allows the model to be able to attend to different things, which is nice. So with that said, now we know about the multi-headed attention. Let's see, I've already said that a lot of times, the problem that you have in this approach. So we still have one problem that you haven't solved. Do you remember that? What was the problem that we said we will solve in the end?
Ordering.
Yes, exactly. Ordering. Yeah. So now the way that we are doing here, like here, there is no ordering, like you are just mixing everything. So we need to have order because we are working with time series data. And actually, if you just train a transformer like what we did, it would be trash result. So it would not work. We need to introduce ordering. But we know that ordering cannot be introduced into the architecture because the links between them are not proper. We don't have links between the cells so that we know the order. So we need to introduce it externally. We need to add something to the data that specifies the order of each cell. There are a lot of different ways to do this. We will quickly go over them. We won't go over deep because also there's a very big like discussion on which max formula you need to use, but we will introduce it and then you can use functions in PyTorch to help you with that. So we call it positional encoding. That's the main way that the authors of the transformer paper try to use, of the transformer papers. So you have the input. Like here, we want to translate Je suis étudiant into I'm a student. Sorry. Okay. So Je suis étudiant. We want to convert it to translate. You have the embeddings. This is what we already had, right? Until here, this is what we already had. We just convert the words into embeddings, and we will see how we do it on Monday. Then instead of just giving it to the encoder directly, you add a vector called the positional encoder that is a vector that specifies what is the position of that word in the sentence. Imagine we have a vector that is different if the sentence in the first position, in the second position, and so on. We add that vector, and then we come up with an embedding with time signal. And then we pass this to the encoder. It might seem a bit weird because you say, well, if we just add a vector, is that going to work? Because you just add a vector and just again mix the numbers because those numbers are added to the numbers of embeddings. And actually, in practice, it works. So maybe it's not very good to say why it works because these are usually not provable things. People just tried and saw it work. And yeah, it works. So you just add a positional encoding. The positional encoder could be designed manually by yourself, or could be based on some formula, for example, cosine or sine waves or these kind of things that have basically the repeated positional encoding. But that's topic for another day. Maybe we will touch it quickly on Monday session because we need to, I think, introduce it for one of our NLP tasks. But I will get deeper into it maybe later. So let's see, with positional encoding and with all that we had, what is the final version of the encoder? There's still one thing that I haven't told because there's also a layer normalization that we do here and an addition. Let's see what's that. We had the input vectors and we had the positional encoding, right? We arrived at the vectors that now are not only about the words, but also about the positions of the words. Then we apply the self-attention layer, as we saw, and then we arrive at Z1, Z2. Here we do a layer normalization. This is not maybe necessary, like the transformer would also work without that, possibly. But people do it because normalization is always good, as we talked about it last day. And you not only normalize this, but normalize the sum of these and the inputs. So basically, again, this is just a residual connection that is not maybe useful to have, but it will also be able to directly also have the input in the normalization as well. This is how they did it and it worked. You arrive at new Z1 and Z2, you have the feed-forward networks, and then you again have a normalization layer, which is again the same layer. So it's basically input, self-attention, layer norm, feed-forward, layer norm. So you have a two-layer normalization after the self-attention and after the feed-forward layer. Fine? It's just how it's implemented. Again, it's not different, but it's how it's implemented. And the decoders are also pretty similar, as we just saw. So you again encode, again you put you add the positional encoding. You put this to the decoder, but you also give the output of the encoder as well. So you turn, you basically give the output of the last, and you give the output of the last, basically each cell outputs one word, which you also inputted to the decoder as well. So the decoder also gets the input as well as the output from the encoder, as we just saw. So here it's we saw this part. This is repeated. Input embedding positional, the attention, layer norm, feed forward, layer norm. Here is the decoder part. So again, we have the output embedding, we have the positional encoding, fine. Here, from this part is similar to the encoder, right? We have the multi-layer attention, layer norm, feed forward, layer norm, all fine. However, we have another attention that also attends on the output tokens until now. Why this is necessary? Imagine you want to translate a sentence like I am a student to just read it down. When you are outputting the last word of the translation, it's not only useful to see the whole English input, but also the words that you were also translating until now. Like, for example, if I say like I am a student to je suis étudiant, when you want to also output the word étudiant, it's also maybe useful to see je suis as well. Because in translation, you not only attend to the English sentence, but you also attend to the partial sentence that you are making over time, right? This can be useful. Maybe not very useful in this example, but it can be useful in other examples. So you also need to provide the output. However, imagine you are translating this word. The idea is that you don't look at the words that come after that, because you don't know yet how to, what would be those words, right? So you basically mask these words, which means that you basically forcefully assign a weight of 0 to these words, to words that come after the word that you are predicting now. We call it a masked multi-layer attention. By masked, we mean basically the future tokens are masked. They have a weight of 0 so that they have no effect on the output, as we might expect in the real world. Because the computer does not understand, we does not understand, please don't look ahead in the future. We just have to set the weight to 0 so that it works. Then, after all of this, we have a linear layer, a softmax, and then we have the output probability. Why do we need the softmax in the end? Why do you need the softmax in the end? Exactly. For example, we want the classification, we want to say if the sentence is positive or negative, we want the probabilities, right? So whenever we want probabilities, we need the softmax, we just have a softmax in the end, we get probabilities, and this is transformers in 1D. That's it. Questions? Fine, fine. Perfect. Also, let me check the chat. From time to time, nothing. Perfect. So this is transformers in one view, just for conceptual. As I said, we will get into practical, more practical approach on Monday, but this is a conceptual thing, maybe, mainly. What did we achieve with all of this? Let's see. This is a comparison of RNN, CNN, and transformer on translation quality from English to French. This is like the very first basic transformer. As you can see, transformer is like of course, from the plot is pretty obvious that transformer are doing better, but at the time, still the differences are low. Now you see like how GPT is able to solve all the questions of all of our courses. Actually, we just had it could end. Oh, maybe I mean it's improving, right? Yeah, it's improving. Of course, yeah, it's not yet replacing humans. We still have had to GPT replacing human. Maybe they will never. I don't know, because we will lose our job if they do. But they are way more capable than what we had 5 years ago, right? So transformer is gonna work. Like we see, this is nothing but when you put it at a scale, and we will see how GPT is trained. We will see it on Monday. You see that transformers have a long way to go, and still basically every day we are hearing new news on what people are doing with all of this. So that's pretty exciting. We have two more topics to discuss today about transformers. One is transfer learning and one is vision transformer, and then we'll be done. So I assume that we'll be finished before 6, so that we won't take much from your time. Let's see. First of all, transfer learning. This is also a very common idea that was introduced in the new era that changed a lot on how models are. Did you learn transfer learning already in the camp? I don't think they have said that, right? Transfer learning. They haven't said that in the bootcamp, I assume.
So it's really quickly.
Sorry?
You said really quickly.
Oh, so very quickly. Okay, so I will explain it a bit more here in the context of transformers specifically. So you can, when you have a model, you can just look at it as a very big black box that you just give an input and provide an output. However, you can split the model sometimes into a body and a head. It depends on where you split it. Like there are a lot of ways to do it, and we will see one concrete example in the empty lecture. However, in general, you can split the model into a body and head from one point. And then you can consider that the body comes first and the head comes second. The body could have the main weights of the model, and the head could be task specific. Why do we do this? Imagine you want to train two models on two different data. Like, for example, a model to translate English to French and a model to translate English to German. You have your domain. This domain is English to French. This domain is English to German. And then you train one transformer for English to French, train one English to German, and French. This is what we already know, right? However, there are things that are common between these two models because both of them need to understand English, and they're only different in how they translate to the target language. We have a lot of data in the world that are in English, but not in French or German. So if we could split the models such that one part of the model only takes care of understanding English, and the other part takes care of making it to German or French, maybe we can have a better first part that we train it not only on English to French data, but also on the English to German data, because it's the same between these two tasks, but we keep the head task specific. That's the general idea. So here we have two domains. We have one body that we use for both tasks, but for the head, we have one head that outputs in French and one head that outputs in German. The body is the same. And actually, this turned out to be useful. Because sometimes, because of the things that models share, you can have bodies that are trained on much bigger data, so they are powerful, and then you just replace a small head based on the data that you have, and you turn out to have very good models. We call it transfer learning because you're transferring a model from one domain to the other by keeping the body but changing the head. And it's also useful when you don't have a lot of data in one language. Imagine you are a specific language in a small country that not a lot of people speak, and you have very limited data. If you want to train the whole model, maybe it's not enough for the model to converge well or to backpropagation to work well. However, head is smaller. So you keep the body from a similar language, for example, and you just replace the head and train the head. So you freeze the body. We usually say freeze the body. It means that tell PyTorch to not to change the weight of the body and just train the head on the new data that you have. And that works. Like people have seen that it works. So as we said, the procedure is to train a model on the vast amount of data, like very, very big amount, because you are doing body only once. So you do as best as you can to have the best body possible. Then for each specific task that you want to do, you just train the head on that task. And that's it. As the book that I love says, during training, the weight of the body learn broad features of the source domain. But for specific features of each domain, you rely on the head. You might think it's a bit counterintuitive, but in practice it works well. And the main thing is that it allows much less training data to be effective, because you only put your resources and everything to have a very good body, and then in the head is smaller. Head is usually smaller than the body. So with a small set of training data, which is not very large, you can have a head that works, and you just attach it to your body, and you have a good model. And with that, you can use a lot. And actually, OpenAI was one of the pioneers on this way before, like around 2017, 2018. They were one of the pioneers. And that actually turned out to be also useful in the future work that they did for GP. Also, I think they also use these kind of things as well, like the fine tuning. We also call it pre-train and fine-tune. That's also another way that you hear this a lot. Pre-train means basically training the body. So it's before the main training that would finish the thing. Fine-tune means to basically tune your model to your specific task, which means to update the head to be able to fix it for a specific task. We will see examples of pre-training and fine-tuning also on Monday as well, so stay tuned. But this is the general idea. Any questions on transfer learning? Fine.
So you like pre-train the body and then you just like freeze the body and keep training on your own little data, but
Yeah.
meanwhile just doing backpropagation on the heads, right? Or
Exactly. So for the first part, you can also train head as well. Like imagine you are training English to French, you also train the head, but then you replace the head and freeze the body and train the head again for another task. Exactly. So you just do the backpropagation on head for each of the subtasks. Just do backpropagation on the body once in the beginning, then you freeze the body, and the backpropagation is only done on the head. Exactly. Right?
okay, thank you.
Yeah. So this is the general, I mean, there are a lot of variations on all of this, right? But this is the main idea, and most people do transfer learning, like one body and one head. Perfect. So in the some time that we have, we will have a quick introduction of vision transformers. And then for text transformers, it will be longer, so it will be next. Until what we saw, transformers, and basically all of the RNNs and what we saw in the past 2 days, were on time series data, right? However, transformers also work on non-time series data as well. It's actually vice versa. If it is time series, it can be worked with transformers. But you know what I mean, right? That is always correct. Like it is time series, we know we should apply transformers, but not vice versa. However, for some tasks, and actually it turns out for a lot of tasks, transformers also work. And one of them that we will could go over it quickly today is for computer vision, for understanding images. We call it vision transformers. So this was this famous paper, and image is worth 16 times 16 words. It was a paper from Google Research in 2021. So it's like a relatively new thing. In this paper, they have the idea to use transformers to be able to train models to classify images. For example, imagine you want to classify if a person in the image is sad or happy, or if a certain plant is has a certain disease or not, or anything you want to classify. What they do is that they first split an image into certain patches. Like if this is the big image, you just split it into patches, like subparts of the image. You flatten them. We will see now. Like I will first give an overview, and we will see in details. We flatten them, and we convert them to linear embeddings, which are lower in dimension. We then add positional embeddings. We give them to a normal transformer, and we also use the same transfer learning. So we first train on a lot of images, and for each task, use transfer learning. So let's see in details how it works. Imagine you have a big image, like the image we saw from EPFL. You split the image into patches, like you see how it's done here, right? For example, you can split the image into 16 patches here, as it's done here, or it can be more or less. Each of the patches is a subpart of the image. Why do we do this? Because images have a spatial awareness. By that we mean, in each image, the parts of the image that are close to each other have a certain meaning. Like imagine in the picture of the EPFL, all of the Rolex would be in one patch. So it's fine. Or at least if it's not in one patch, it would be in two patches or something like that. It's not that if we just randomly shuffle the image and instead of doing the patching, we will get a very big image and we can't do any special awareness. But usually people have found that if we split the image into 16 parts, at least one of the parts would be the part that is useful for us to find the classification result. Imagine it's the room of the classroom, or maybe a picture of me, and the model wants to classify if I'm happy or sad. So the patch that my face is in would be the relevant patch for the model that the model should pay the most attention to. So this is how the attention works in image, right? You first split into patches. Any questions here before I go? Perfect. So how it is done? Let's play with numbers a bit to see how it's done. Any input image has a height and width, right? So it's like two-dimensional, and as also a third dimension. What is the third dimension? It's the RGB values of the image, because each of them have three values, right? It could be red, green, blue, like they have the three different values per cell. You all know RGB, right? So it's basically 3 dimensions per image. So it's like a 3D matrix. And we want to divide it into fixed size patches. So imagine you have a picture, 224 pixels times 224 pixels. It's a square image. And it has the dimension of 3 for the other dimension because it's RGB, like 3 values. We want to split it into patches of 16 by 16. How many patches do we need? We have 224 pixels. Like, so this is the big picture that we have. We have 224 pixels. And then we want to split it into patches that are 16 in size. So each of them are 16. So how many patches do we need? We need 224 over 16 here times 224 over 16 there. So if you calculate it, it would be 196 patches, for example, for such. It's very easy, right? You just come up with this number. Usually it's a base of 2, I think, and then you find the number of patches needed. And then each patch is 16 by 16, but however, it's actually also the third dimension as well, because you are also keeping the red, green, blue values. So each patch, you convert it from a 3D matrix to a vector of size 768, which is 16 times 16 times 3. So basically, you flatten each patch into a vector. That's how it is done. And then you pass them through a fully connected layer, because that's how you do it, like to just transfer it, be able to learn some weights from the input patches. Any questions here until now? Like we just split the patches, right? These are basic math. Any questions? Perfect. Let's see if also anything in the chat. No? So we also have to add positional embedding, because in convolutional neural networks, if you remember how they were made, we didn't need positional embedding because we are literally reducing the picture and keeping the size of everything. But here, when we pass them to the transformer layer, the order of the patches are shuffled. So we need to add, again, positional encoding to each of the patches, similar to what we did with text. Then you just pass it through a normal transformer. Again, you can have multi-headed self-attention, layer normalization, feedforward network. Basically, everything that you also had in transformer, you just pass through it. And then, however, it's normally an encoder on the transformer, for example. You could have, imagine it's like an encoder transformer because you are not generating a text here. That's another topic that we will see later. We also, in addition to all of these patch embedding sequences, we also add a certain token as the classification. And we check the output of that token to see what's the result of our classification. Because in the text, we didn't need this, right? We wanted to just translate, I am a student to just étudiant. So we didn't need another token, but here we are inputting the picture, and we want to have the output of one of them to tell us if the classification is like the picture is happy or sad, or like has a certain disease. So you add the classification token, and you pass the output of that token through a multi-layer perceptron to a neural network. I don't know, you call it NLP, to a neural network to produce the class predictions. And you have a softmax in the end. So that's how it works. Any questions? All right. So what you do is pretty simple here. Again, you split the image into patches, you flatten them, you add positional embedding, which is very important because otherwise you will lose whatever in the picture. So imagine like you have a picture and if you lose the order of patches. If you ask a question of a model that what is on the right side of the picture, it has no idea. So it's better to have positional embedding. Then you pass through a normal transformer with all of the features that you have. You add the classification token, you put the output to a neural network, softmax, and produce the probabilities of class prediction. So as you see, you can apply the same method to images, but you just need to do the patching thing, and the rest is the same. With that said, is computer vision solved? Of course not. Transformers are never a solution to anything. Vision transformer has actually mostly a better performance, especially on large data sets, compared to CNNs. It's pretty nice. So when it came out, many people were saying, okay, we don't need CNNs anymore because vision transformer is better, transformer architecture is better than CNN, so we don't need CNNs anymore. However, there are two problems. First of all, like normal transformers, vision transformers are also computationally expensive because we saw how many things that we need to do. And also, the more important thing is that, like normal transformers, again, we need a lot of data. So on the fact that we don't have much data, actually CNNs work better. CNNs usually perform better on a small data set because they have way fewer learnable parameters. And that's the main difference. And also regarding images, they're also usually more difficult to find than text. If you want to have text data, just go to Wikipedia, just go to Google and search a lot. But how many pictures do you have? Like imagine you want to find a model to classify happy and sad pictures. You need to collect lots of pictures from people, and you need to go through data consent process because people might not want to have their picture scanned for a model, right? You should get an agreement for every person. Do you want me to scan your face? A lot of things, right? So usually getting images, collecting images in a real project is way more difficult than collecting text on average. So usually you don't have lots of pictures, and thus CNN usually work better on small data sets. However, there is one way to circumvent this. Anyone remembers that? Sorry? You mean transfer learning? Sorry? Yeah, exactly. The partition, exactly. So you can use the exact same idea. If you have a head and body, you just collect lots of pictures. So we have like data sets like ImageNet that have basically tons of pictures of different things. You train a very good body based on them, and then you just train your head, fine-tune your head based on the specific data that you want to have. And that actually has shown to be pretty good. But still, in some places that you have very small data, maybe CNNs work better. So it's something that you always need to balance and check for. There's not only one solution to everything. Transformer is not the solution to everything. In each problem, maybe a simpler model such as an RNN or CNN could work better. So you should check out for every task that you have. Any questions? Perfect. All right. 5:58, 2 minutes early. So yeah, I think I said what I want to say. As I said, we try to keep it a bit shorter, but Monday session would likely be longer from what I've heard, because I mean, you would have also wanted to have a poll on splitting that, but I think there's no much time left on the rest of the week because there are also other sessions. And we want to finish it next week before the semester starts. So I think that's a little bit longer. Maybe it would take until 7 or so. Not longer until 8, but maybe until 6:30 or 7. I hope I can finish it on time because I also want to show some code. Today we didn't see any code, but we'll see the code relevant to all of this on Monday. On Monday, we will see a specific case scenario of applying this for NLP. And in the first part, we see how we can convert words to embeddings, because that's one part that we did here, and it was actually pretty important. Right here. Where is it? Sorry. Here, like this, we convert this word to vectors, right? We see how we should do it in the best way, because we don't want to just be randomly, we want to do it in a way that works the best. And then we will see two main architectures based on transformers that people have been using to work with NLP. We will see basically an encoder-only version, which is BERT, and the decoder-only version, which is GPT. And we will see how they are made. And then in the end, we will have a quick recap on what have been the new things going on there in the past 2-3 years. What is OpenAI literally doing all this time, and how they are improving GPU over time. So this would be a summary of Monday. Any questions? And then after that, you will have session on computer vision. I will not be there anymore. So I will just be on the Monday one, and I think on Tuesday and Wednesday do the other people. So you will see more stuff on computer vision and I think audio processing. Perfect. So thank you so much. And have a nice day.